Hello and good morning, good evening, good afternoon, everybody. Thank you for joining to this Neo4j live stream today on pathfinding algorithms using Neo4j. I'm very happy to have Mehul with me. Mehul, here you go. Thank you for joining, Mehul. Hope you're doing well. How is it going for you?
Yeah, it's great to be part of this live stream. I'm doing great, and today we'll discuss about pathfinding algorithms in Neo4j. Very excited for
Yeah,
this.
me too. It sounds very good. I'm very excited as well. Excuse me. Yeah. Before we dive in, I'd like to make a little announcement. Obviously, you probably have seen this at the bottom of the page. Neo4j Notes is coming up. So I'm very excited to talk about Notes a little bit before we actually dive in. So it's going to be on the 16th and 17th of November. It's our online, live online practitioner or developer data scientist event. And you can register on our new homepage, which just went live earlier today, where you now find some more details. And up until basically today, 10 minutes ago, you were unable to register, and we couldn't give you so many details. Now, if you check out the website, there is an actual agenda, a preview of the agenda, a keynote session, and some other information. And yeah, I'm very excited about this, and I'm looking forward to Notes. I really excited, and I hope this will be a good event and very interesting on so many fronts that I'll think depending on no matter where you're from and what you're interested in, you can you will find something interesting. I'll quickly switch to this more dynamic view here to show you what the page is like. And here you see what to expect. Here you see Nicholas Christakis is our keynote speaker. He wrote a couple of books. This one is probably his best known one, Connected: The Surprising Power of Our Social Networks and How They Shape Our Lives. And this exactly is the topic he will discuss in the keynote. And featured speakers, some highlights. Check it out yourselves. Workshops. We plan a couple of workshops ahead of Note starting on the 19th of October, where we can also join for free, and then some highlights from previous years. But check it out. Links in chat. It's going to be good. Good. All right. But now, pathfinding algorithms using Neo4j with Mehul. Mehul, maybe before we dive in, do you want to share a few words, say a few sentences about who you are, what you do currently, and maybe what what has brought you towards Neo4j and towards graph technology? What was your how did you discover it? Why is it why did you find it interesting? And a little bit about your graph journey, maybe.
So hi everyone. This is Mehul Gupta. I have been working with the Development Bank of Singapore, DBS Bank, for last 1 year as of now. Majorly, I'm working as a data scientist here, working on different algorithms like some R&D projects, etc. Talking about Neo4j, so like I was exploring about graph databases and graph analytics, and the first name that came was Neo4j only. So I've heard it from my elder sister as well, and eventually I just deep dive into it and seeing it's one of the most concept that I've come across. Like I have been a regular blogger on Medium. I'm one of the top AI writers on Medium as well. So I've been exploring different things, and this time I just bumped into graph analytics. And to be honest, it was so interesting that I ended up writing a 6 blog series on that for about a couple of months, and then eventually Alexander just highlighted and he wished me to deliver something on the project that I have been working on around the AI network. It's just a dummy project just for exploring, and I was more than happy to contribute to this Neo4j live. So yeah.
That's cool. Yes, thank you. I just shared your the link to the Medium blog series you just mentioned, and I think it starts with part 1, and obviously, like you said, goes up to part 6. So it's a really cool overview and introductory session content. So if you're interested in all of this, read up on it, because it's very rich in content and lots of interesting parts in there. And so it's very cool that you did that. So thank you for writing these. And obviously, if you want to read up on this, check out the Medium blog post. This is where we all wrote everything down. Graph algorithms and the graph data science library is a very important feature of Neo4j. And how are you using it currently, or do you have any tips for, because you wrote this intro session, maybe any tips for beginners as a short summary before we dive into the pathfinding part? How would you recommend for beginners to start with graph data science?
Mhm.
Michiel? Did we lose you?
No, not really. Like some minor issues. So to be honest, so like a graph database in itself are pretty unique in nature, and you might not be able to like find out some exact solutions in real world. But eventually, when you will look into some social media sites, some data sets around where you need to form networks, basically this is the go-to place too. Neo4j also has a graph data science library called as GDS library that has implementation for multiple algorithms that you might find interesting. From that, the visualization that Neo4j provides is just amazing. To be honest, for any beginner, first of all, try to figure out that you wish to work with. Like for example, I wish to explore the airline network in India, and eventually I went on with that. You can go with your Facebook friend network, your Instagram network, or some other social media net that may excite you, and eventually you can get started. Was some demo projects are also present, that some demo videos are present in Neo4j itself. You'll be able to figure out a lot of analytics, a lot of insights about that straight away. So yeah, my suggestion would be to figure out a problem statement that excites you, and eventually the rest of the things would be taken care by Neo4j, because the Cypher query that comes in is pretty easy to use. And yes, the demos are present are pretty fine. Like a beginner can quickly learn it up. So yeah.
Yeah, exactly. I think that's a great suggestion. In general, if you have something you are not quite sure how to go about, and then if Neo4j and graph databases are new technology for you, then trying picking a data set you have worked with before, you are somewhat familiar with, is a big asset. So you can go about with this and import it, play around with it, give it some new spin, but you know the data, you know what's in there. You don't have to try something new with a data set that you are not familiar with, which you don't know quite what is all about. But then you explore the data, and then you will find some information in there that I'm pretty sure you are surprised, maybe. Okay. Well, yeah. With that, I think I'll hand it back to you, Mihul. Let's go and look at the pathfinding algorithms. I will post the link to this Medium post as well into the chat. So this is what we're going to talk about now. And yeah, and then also, by the way, if you're wondering, the internet connection for Mihul is sometimes a little bit flaky, so that's why we decided to switch off webcam to save some bandwidth and to make the best of the internet connection. So I hope this is okay, but still, this should be fine. If you have questions, if you have comments, if anything is interesting for you, and particularly about this all, please don't be shy. Use chat and type it in. We try to answer a couple of these if possible. Otherwise, obviously, I can always point you to our community page, where we have a very active community on all things Neo4j and around there. So if you have any further questions, go there. All right. Ew.
So let's get started with graph analytics, pathfinding algorithms using Neo4j. So before we start off, there are a few things that we will be requiring. Like I will bring you a brief summary of what we'll be covering in this session, and a few prerequisites that are required. So basically, in this session, we will be considering a few set of algorithms. One Dijkstra, I think one of the most prominent shortest path algorithm. Apart from that, all shortest path algorithm, Yen's K shortest path algorithm, A star for shortest path, and SSSP, triple SP, that is single source shortest path algorithm. So we will be discussing a bit about all these algorithms and then its Cypher implementation using the GDS library in Neo4j. A few prerequisites that are required are basically basic understanding of graph databases, Neo4j, and Cypher. So if you don't have it, no worries. It is the second blog in my series. You can go and check out the first one. The link is in the description itself. We need to add two plugins basically. One is the Graph Data Science GDS Library plugin and the APOC plugin. So how are we going to add it? So I have added a small video around that. Once the Neo4j desktop app, you can click on the database. Apart from it, you can on the right hand side, a pane appears that is the plugins, where you can install these two plugins that are required for this session. One is APOC and another is Graph Data Science Library. Once you're able to do that, we need to make certain changes in the Neo4j config file as well. So how to open that config file? I have again added a small video for that. You can go and click on the three on the top, and you need to add these two statements in the end of the configuration. Allow us to load a file from APOC library. Uh, Once we are done with that, let's first of all understand the data set that we are going to use, and eventually how are we going to convert this particular CSV into a graph database. So this is a particular CSV that I have got from the site of the government of India. Eventually it consists of the flight network in India alongside the vendor which is providing this airline. So particularly I have picked out SpiceJet for now, because else if I have been using the entire all the vendors, then it would have been a very big humongous data set. So eventually I just picked out the flight network for SpiceJet, where you can see the origin of the flight, the destination of the flight, the distance between the two cities, the latitude and longitude of the origin city. That is why you can see repeated values coming in the next, because the origin city is common for now. Now we will understand how we are going to convert this CSV into a graph database. Uh, so first of all, the nodes that we would be forming would be the city names, the cities. Now cities would be having three attributes. One is the name of the city, the latitude, and the longitude. Apart from that, we would be the relationship that we would be establishing between the two nodes would be the flight. You can call it as air distance. You can call it as air, like flight distance, anything you wish to call. I have called it as flight. And the attribute of this relationship flight would be the distance, as you can see here. So I will show you like how it actually looks like. I have added all the demos here. Alongside latitude and longitude will be the property of the node city that we would be creating. So I'll be sharing with you the query also and all the stuff that is required. So no to worry about. So first of all, we would be loading this CSV into a Neo4j database. So for this, what we need is to do is that we need to first put this CSV in the import folder of the database. So if you remember, when we changed the config file, there was an option for folders and then an import folder option. So you need to put this CSV in that file, and then you need to run this Cypher query. So I'll be explaining you what this Cypher query is all about. So the first line of the query, call apoc.load.csv, calls out this CSV and loads it into the memory. Yield list as item. What does this statement does is it eventually reads each and every row of this CSV that we have as a list item. Now the three statements are basically purely Cypher that which we would be using to create the graph database. So here we are providing a label city to the nodes that we are creating and assigning it three properties: name, latitude, and longitude. And items, as you can see, if you look at here, the index 0 becomes our origin, index 1 becomes our destination, index 2 becomes our distance, index 3 is latitude, and index 4 is longitude. So accordingly, we will be assigning these properties to the node city. We'll be again creating another city object with item 1, which is a destination, so that can able to finally build out the relationship flight. with the attribute distance between n and m. So basically, n is our origin, m is our destination, and flight is the relationship that we are establishing. Now, once you are able to create this, we will be getting a graph like this. As you can see, we are having all the city names in green nodes. You can see the red arrowheads coming in with some numbers written on it. These numbers are the distance, as we discussed in the relationship that we have created as of now. So similarly, as you can see, it's a very big network that we have created for SpiceJet network in India. So now we are done with the prerequisites. The second step would be to create a graph projection. Basically, graph projection, the idea of graph projection is basically coming from views in RDBMS. So in view, what we do is that eventually we take a sliced version of the original table, and eventually we try some operations on that so that we are not altering the original data. So accordingly, we will be creating a graph projection named as airline using the above graph database that we have created using the above Cypher query. Now I will be explaining you the how to create this projection. It's pretty easy. We will be calling again the graph data science library gds.graph.project. We will be giving this projection a name, airline, city, alongside the properties that we wish to use. So eventually assume that we might have 4 to 5 properties, but we wish to use just 2. So we can do it here. Alongside flight, the properties is distance that we are using with that relationship, and the orientation is undirected. So what does this mean? So eventually, if you have basic understanding of graphs, so graphs can be of two types, basically directed and undirected. In undirected means that there are no arrowheads. Basically, you can go from node A to node B and node B to node A. And in case of directed, depending upon the arrowhead, we have just one direction to go. So we would be considering this as undirected graph for now. Now, jumping on to our first algorithm, that is the Dijkstra algorithm. So I really don't think that this even requires some introduction because it's very common in, algorithm for the shortest path between two nodes in a graph. So we'll be straight away jumping onto the implementation rather than some explanation on that. So we will be first of all finding out the aerial route between Jammu and Darbhanga, the shortest distance between Jammu, one of the cities in the north, and Darbhanga, one of the cities in the Bihar. So eventually, the query becomes is match source colon city, name of the city is Jammu, and target becomes our Darbhanga. Calling the algorithm from GDS or shortest path from the Dijkstra stream, we are calling the name of the projection. We are providing the source node as source that we've already fetched out in the first line, target node that we have already fetched out in the first line again, and the relationship weight property. So basically, when we are calculating the Dijkstra, we are considering the weight of the edges that we have got. So that would be the distance. Now we get a yield statement from it, that is index, source node, target node, total cost, node IDs, cost, and path. So I will be discussing what each this output coming out. So index can be ignored. Source node and target node remains the same that we have already provided as Jammu and Darbhanga. Total cost is the total cost to reach from the source node to the destination node. Node IDs is basically the path that the Dijkstra has followed to reach from the source to the destination. Cost is to reach to each node in the path, the cost associated with each node, and path is finally used to visualize the path that we have got. So you can see return being used, and then we have made a certain transformations down the line. So what are the transformations that we are using? So the GDS implementation of the Dijkstra returns the source node ID and the target node ID. So using the node IDs, using the GDS.utility dot as node, we are trying to fetch the node object from the node IDs that we have got from the algorithm. Similarly, for target name, total cost has remained the same, and we are trying to fetch the node names from the node IDs that are following in the path that we have got alongside cost and node path as discussed earlier. So this is the output that we got finally, Darbhanga to Delhi to Jammu. So the shortest path following the Dijkstra algorithm that we get is from Darbhanga, you need to go to Delhi, and then you need to go to Jammu. And you can also see the distance being written on the red arrowheads that we have got. Similarly, I've also tried to run it on Pondicherry and Kandla. So Pondicherry is basically in Chennai, is in Tamil Nadu, and Kandla is a port town in Gujarat. So here the path becomes a bit different. From Pondicherry, you need to go to Bengaluru, then to Mumbai and Kandla. So this is how easy this implementation is, and using this, we have figured out the shortest path between two major set of cities. Now, one thing that you might have noticed is that the arrowheads appear a bit ambiguous. like somewhere it is going as somewhere it is going there. So eventually I was trying to figure out, why is this happening. So this is happening because in Neo4j, in terms of visualization only, so like in terms of logic, so it is able to figure out that the graph is undirected, but in terms of visualization it has to be directed only. So that is why we are getting some arrowheads. So kindly ignore these arrowheads and consider them to be completely undirected. Now moving on to our next algorithm, that is all shortest path algorithm. I think I'm in line with everyone, right? I'm not missing out on something. Alexander, can you confirm?
Yes. Yeah. It's all good.
Yeah. So now moving on to the next algorithm, that is the all shortest algorithm. So it can be taken as a hybrid version of the Dijkstra. So what we are doing here is that we are not taking any source or destination node, but we are trying to figure out the all shortest path between each and every possible pair in the graph network that we have got. So if we have got 10 nodes in the graph, we would be calculating the shortest path for 100 node pairs, even for each node where that is possible. So the only difference between the Dijkstra and all shortest path is that in the Dijkstra we are trying to calculate the shortest path between just a pair of node that we are providing, and in all shortest path we are calculating for the entire entire graph database that we have got. So the implementation changes a little bit. So you can see that earlier we were trying to fetch out the source and the destination nodes. Now we are calling the all shortest path algorithm gds.alpha the all shortest path dot stream over the graph projection that we have created already, and just providing the weight property as distance. Now it yields us three values, that is the source node ID, target node ID. So basically, there is a point that I wish to discuss, that is what is the difference between yield and return. So it is quite similar to what we have in Python also. So yield gives us a generator object that can be read one by one, and return gives us an output on the screen itself. So assume it to be a set of entries that we are getting. So it would be a list of 100 entries that we have got, and using return we will be reading them one by one. So there we are in all shortest path we have used two filters as of now, just to for the output purpose. One filter is that where gds.util is finite is true. Why we are using this filter? Because it can be the case that we don't have a path between two possible nodes in the graph, right? Two cities are just not reachable. So we are trying to ignore those cases. So that is why we are trying to keep is the distance is finite. Second filter that we are using is that the source and the target should not be same. So as I told you earlier, that if we have got 10 nodes in the graph, and we would be calculating it for 100 nodes, 10 cross 10, 100 pairs. So this will include cases like Delhi and Delhi, Pune and Pune, Hyderabad and Hyderabad. So even the source and the target node becomes the same. There would be cases like that. So we are trying to ignore that in the output. And then what we have tried to do is I have applied a filter for Amritsar. So what I wish to do is that I wish to see the smallest distance to each and every city in the graph from Amritsar, which is in Punjab. So this is the output that we have got for Amritsar. That is a source, the target is a city, and we have got the distance using the all shortest path. It's a long output, that is I applied a filter on Amritsar, else we could have gone for the entire output. Now there is a slight intervention that I will do is around the single source shortest path, triple SP algorithm, and the all shortest path. So triple SP algorithm works the same way as all shortest path, but just for one destination. So what we did in all shortest path is that we first of all calculated the shortest path for all the possible node pairs, and then we applied a filter for Amritsar. Now in case of single source shortest path, what we can do is that we can simply provide that one city from which we wish to calculate the smallest distance for every other city. So that is the difference between the two. In single source shortest path we are providing the origin, but in case of all shortest path we are not providing any origin, and rest is the same. Moving on to the most interesting algorithm, I think most of the guys might not also be knowing, and I will be discussing it a bit. The logic behind it is the Jens K shortest algorithm. So at times, what we wish to have is that we wish to have multiple shortest path between two places. So if you remember Google Maps, so at time you might see multiple path coming to your destination. So Jens K shortest algorithm helps us in finding that. It helps us in figuring out multiple shortest path between a given source and destination. So I will be giving you a brief about how Jens K shortest algorithm works, and a very brief and not nothing mathematical. So it also follows. It can be taken as a hybrid of the Dijkstra only. Assume that we wish to calculate the Jens K shortest path Yen's two shortest path between nodes A and E. So first of all, what we would be doing is that we will be following the Dijkstra for the first iteration. That would give us the path ACE. I have already calculated it, but you can also calculate. You will find the same answer. Now, when we are moving on to the next shortest path, that is the second shortest path, what we would be doing is that all the nodes that we have got in our previous answer, that is in the shortest path, we got A to C and C to E, we will be setting these nodes as infinite one by one. So for example, as we had AC and EC in our shortest path, so in the next iteration, we will be setting AC as infinite so that we can't consider it back in the Dijkstra algorithm. So now the shortest path, once we have set this as infinite, would be A, B, and E. You can calculate it. I've already calculated. Similarly, the next time we would be setting E and C, the edge between E and C as infinite. So what we have done is that whatever path, whatever no edges that were the part of the previous shortest path, we are trying to set them as infinite one by one. Once we have set this as infinite again, then also we get the shortest path as A, B, and E. So eventually, in this case, so what we got is we have got the same shortest path after setting both the different edges as infinite, but in many cases you might get different shortest path. So once you have got multiple shortest path, whichever path is the shortest one amongst all those shortest path, after setting each edge infinite one by one, we will be selecting that as the second shortest path. Similarly, the third shortest path, the fourth shortest path, and so on and so forth. I think this should be give you a sense how Yen's K shortest algorithm work. Now we try to figure out the Cypher query for finding three shortest path between Hyderabad and Mumbai. So we will be discussing the Cypher query for that. It looks pretty similar to what we have in the Dijkstra. So again matching, we will again trying to fetch the node which has the name Mumbai and fetch the name of the city which has the name Hyderabad. Next, we will be calling out gds.shortest path.yen.stream, where we are inserting the name of the projection, graph projection that we have made, the sword, the target node that we have already fetched out, k equals to 3:3. That means we wish to figure out three shortest path, and the weight property, that is distance. Now it yields the same thing as we have in the Dijkstra, so I would be skipping this part. It's output that we have got, the same format. Again, we are again using the gds.util.as node to get the name of the source node and the name of the target node, and similarly to get the name of the node that are present in the path. So if you see the output, we have got Aurangabad and Belgaum as well. So the shortest path is Hyderabad to Mumbai. The second shortest path is Hyderabad to Belgaum to Mumbai, and the third shortest path becomes Hyderabad to Aurangabad to Mumbai. So eventually, in this visualization, you can see that how we have fetched out three shortest paths given the origin and the destination node. An algorithm that I haven't mentioned earlier, minimum spanning tree. I would be giving a brief on that as well. So minimum spanning tree basically is a path that connects all the nodes in the graph with minimum edges, with minimum weight. So there are two types of spanning tree. One is a minimum spanning tree, other is a maximum spanning tree. A spanning tree with the lowest cost of traversal becomes a minimum spanning tree. So like for example, if you have 10 nodes, we wish to figure out such a path which has the total cost as the lowest one, and maximum spanning tree is just the opposite. So we wish to figure out a path that connects all the nodes with the highest value. So minimum spanning tree can be taken as a solution for the salesman problem that we have heard of, where the salesman wishes to visit all the nodes in the shortest given time. So minimum spanning tree can be taken as an example for that. I won't be deep diving into the logic, but if you wish, you can go and read about Kruskal and Prim algorithms that are very prominent, and you can find multiple blogs on that. That is why I didn't include it in this session. Now moving on to the Cypher query for spanning tree. In this, we need to provide the origin node, because when we will do the nodes, we wish to have one origin to get started with. So here I will be taking Delhi as the origin node. So first of all, again, we will be fetching the node object that has the name Delhi. We would be running the gds.alpha implementation for spanning tree dot minimum. Now, if you wish to get for maximum spanning tree, you can go for maximum dot right as well. You are providing it with the projection name, that is airline. Start node ID. Now, earlier what we were doing is that we were providing it with the node objects. That is, if you remember, we were directly using N and M notations. But now we need to provide the node ID. That is why we are using ID function. Relationship weight property remains the same. Right property, weight right property yields the results something different. So I need to explain this a bit. So if you have noticed in the earlier implementation, we have the function string here. in the end. But in case of MST, we have a function right here. So I will tell you the difference between the two. In case of stream, what we are doing is that we are getting the result then and there in the output world, in the output console of yours. But in case of write, we are not getting the result output directly, but we are writing that result into the graph database itself. So that is why you can see two new properties coming in. That is write property as minST, and write weight write property, that is write cost. So we are creating a new property now, a new relationship that would be minST, and the weight that we are assigning it to is the write cost. So for example, in the we have 10 nodes and we have reached the 5th node. So the total cost till that time for the MST would get written there. So eventually, that is the difference between write and stream. In write, we are writing back to the database, and in stream, we are again outputting the same onto the screen itself. The yield results are mostly the metadata around the query that we have run, missing time, what are the nodes affected, etc. And that is of not much use for now. Now we need to again run a secondary query, that is match and return n. So what we are doing is that in that case, in this case particularly, we are fetching all the nodes and then returning them back. And the blue lines that you can see is finally are the MNST tree that we have formed. So you can see that on the blue nodes, the relationship has been written as MNST. That is the relationship that we have formed newly. If is forming a minimum spanning tree now. So ignore the red lines, assume the blue lines that are coming. So you will notice that each node has one incoming edge and one outgoing edge, because in a minimum spanning tree or a maximum spanning tree, we need to visit each node just once with minimum or maximum cost, whatever is required. Now coming back to our distance algorithm, the last algorithm that I would be discussing is the A star algorithm. Most of you must have heard of it, but I think I would be giving a brief on that again as well. So the A-star algorithm is very similar to the Dijkstra with a slight change. So in the Dijkstra, what we do is that we already have a pre-calculated weights assigned to the graph database. So as we have the distance attribute that we wrote in earlier in our graph. Now in case of A-star, we would be considering two factors. One is the pre-calculated weights, and second is the estimated distance from the current node to the final node. Let me explain this with you an example. Assume that we are standing at node A, and our destination node is E. Now eventually, now if following the Dijkstra, we need to choose between C and B. So the choice becomes, we need to compare these two entities, that is weight AB, that is 2, plus estimated distance between B and D. Why B and D? Because the current node becomes B and the destination node becomes E. That is the final destination where we need to reach. Similarly, for considering AC, the weight between AC is considered plus estimated distance C comma E. Now, you can say that we know the weights between AB and we know the weights between AC, but we don't know what is the estimated distance between B and E and estimated distance between C and E. So how to get onto this? Let's discuss that. In case of Neo4j implementation, what have been used is that the distance has been used. That is a distance between 2 points on a spherical surface like Earth. So if you remember, if we haven't used the latitude and longitude properties that we have written earlier in the database, so we would be using that now. So what we would be doing is that we would be using the distance, if you remember the property that we have written for the weights, and estimated distance would be calculated based on the latitude and longitude of the origin and the destination. So how the query is written, let's come to that. A Cypher query for writing shortest distance between A, using A star algorithm between Tirupati and Leh. So let's try to figure out what is the query for that. Again, we would be matching source node and the target node as we did for the Dijkstra and other most of the algorithms. We would be calling the shortest path dot A star algorithm, having its implementation in GDS, calling the name of the projection. Source node, target node appears the same. Now two new properties that we have added is latitude property, that is lat, and longitude property, that is long. This is because as the GDS library internally implements have assigned distance, we need to provide this latitude and longitude that we have already written in our database. Again, the results that are yielded are same: index, source node, target node, total cost, node IDs, cost, path. And eventually, this is the result that we have got. From Tirupati, you need to go to Hyderabad, to Delhi, and then to Leh. Now, this is the shortest distance that we have got from A star algorithm. Now that's an end to the session. Most of the algorithm that I have taken are like mostly it covers the path finding algorithms in Neo4j and graph databases also. If anyone has any question, I would love to answer that if I'm able to. Yeah.
Cool. That was a whirlwind tour through graph algorithms and pathfinding on airline. Well, I'm on airports. Here we go. Across India. So I think that was pretty cool. I see one question from Ponsemity. I can put it up here as well. Is it possible to have another node label between city nodes and calculate the algorithm even if this node label is not on the projected graph? Yeah, do you know the answer to this one, Mihul?
That would be creating multiple nodes. You can assign multiple labels, and then accordingly you can have a chat with that. So, matlab ki, it shouldn't be an issue. It will create multiple. Like if you are assigning it a different name, so eventually you labels yes.
Yeah.
When
So
you are implementing for the algorithm, and if you are using the projection name, as you saw in most of the algorithms, using projection names. Was I getting stuck?
You were getting a
So
little bit stuck, but I think, yeah.
Okay. So like if you saw in most of the some of the implementation, we were using the projection names directly. So in that case, you might have some problems. But in algorithms where you're directly using graph objects itself, it shouldn't be a problem if you're providing multiple labels.
Yeah, you can always
But what it will
add more
create is that
labels.
it will create duplicate nodes for you.
Yeah. You might have to recalculate, I guess, if you choose different labels. If you depending on what setup you want to use and where you want to go on your initial projection of your graph. That could be a point to remember. Yeah, I don't see any other questions. Let's give it a second or so for people to write any other questions. So if you have anything else for Mehul, then please type it in. I wanted to know, and maybe you had this, but in your blog post, but I might have missed this. The data you used, is it available somewhere? Can people go and download your data set and try to import it in themselves, or is it something that is not possible to be shared?
So Alexander, the dataset is available in two versions. One is on the Indian government website itself, that is not processed.
Yeah.
Also, I have uploaded my version as well, that is a bit processed, and I have provided that link in the blog itself.
In the blog,
So you
okay.
can go
Sorry,
and download that.
I missed that. Sorry.
Uh,
Then that's perfect. So people can download the data from you, somewhat processed, and can play with that. So to follow it up as a
the entire exercise can be replicated completely.
okay, super. That is super helpful, I think, for people to try it out themselves and to get their learnings. All right, question from Ankur. Here we go. What if we don't have predefined distance weights for relationships? Yeah. So if we don't do
In that case, Ankur, what happens is that Ankur is that it eventually counts the number of edges that are coming up as the weight. So for example, if you're calculating the Dijkstra and you don't have weight, so it will count the number of edges that are coming. Path comes edges you rather than the.
You're cutting out a little bit, Mehul. Maybe we try this without the video. Do you wanna try it again?
Okay. Just. Hello.
Yes.
Yeah. So
yes.
What I was saying is that you don't have predefined weights or distance. What happens is the algorithm intakes the total count of edges that are coming. So for example, give an example from the Dijkstra algorithm. If you don't have weights, so it will count the number of edges that are passing in the shortest path. So for if a path has 4 edges coming and the other path has 3 edges coming, so it will take the 3 edges path as the shortest path if you don't have weights.
Okay, cool. Perfect. Thank you for this. Yeah, I think we are at the end of the session today. This, like I said, this was very interesting and very hands on, and I'm a little bit still. You were so fast. That's unbelievable. That was very quick. So maybe people, if you missed something, rewatch it a little bit on a little bit slower speed. But I think it was clear that you're enthusiastic, and it was very clear that then you can, if you follow this on the website, on your blog, that then for processing this along your data, I think everybody can replicate and learn a lot from doing how you did it, and then eventually be as fast as you are. So final comment maybe here from Srikant. I firmly believe in the graph database replacing, can put it up here, replacing relational database for the most part, especially with their strong emergence in data-driven business and easier data collection than ever. There are graph databases coming up as Neo4j with inbuilt analytics, and then it's cut off in these functions. Yeah, so absolutely. So I mean, we obviously believe in this as well. We think that besides RDBMS, relational databases, which will be around for a long time, graphs are the next logical addition to the database world, and we firmly believe that that obviously Neo4j is this offering or this product that will help a lot of people to make much more sense of their data, connect their data, do something, not only storing data and linking data together, and querying data across silos maybe that is happening and getting some real-time results, but also like what we showed today in a more data sciencey background, where you do algorithms, where you do analysis on a more like a machine level machine learnings level, where you then use your data in a new way, and it can work with your data in the same way, or in a much quicker way, without using lots of different tools. You can use the graph as your structure of your data, and take it, store it, but also analyze it, visualize it, and work with your data. So I think, yeah, absolutely agree to this, and we are seeing this developing as we go, and it's becoming more and more prominent. So absolutely, yeah. Do you have a comment to this, Mehul?
Nothing much. I think you pretty much covered everything, and like even Shrikant is like more of a statement rather than a question. So yeah, I'm into it as well.
Yeah. All right. Cool. So absolutely wrap it up. Thank you very much, Mehul, for taking the time for showing us around, and for giving this presentation today. Thank you for writing the blog in the first place. It was cool and to read it. Thank you all for watching, and we will be live again next week. Monday has to skip, but we will do a Neo4j live on Thursday on Ethereum. So that's a cryptocurrency analytics live stream on the Thursday, and on Tuesday I will be back with my dear colleague Jesus on Going Meta, everything on semantics, ontologies, and knowledge graphs. So 2 cool sessions coming up next week. Don't forget to register for notes. Thank you very much, Mehul. Thank you for your time. And thank you all for watching. Take care, everybody. Bye.